For this video, we will find the x-coordinates, if any, at which each function has a discontinuity. We will classify each discontinuity as removable or non-removable. Let's do a quick side lesson. Let's say we had the function f of x and it was equal to x plus 3 times x minus 2 over x plus 3 times x minus 4. Notice that we have a common factor in the numerator and denominator. When you have a common factor like this, which could cancel out, this is where you will get a removable discontinuity. In this case, the removable discontinuity is at x equals -3, because that's what you get if you set x plus 3 equal to 0. The non-removable discontinuity will come from the remaining denominator. In this case, the non-removable discontinuity will be at x equals 4, because that's what you get if you set x minus 4 equal to 0. You should also know that a removable discontinuity is going to be a whole, and a non-removable discontinuity is either going to be a jump or an asymptote. In this case, it's going to be an asymptote. So we're saying there would be a hole in the graph at -3, maybe something like this, and meanwhile there would be an asymptote at 4, which might be like this. So maybe this piece of the graph would look something like this. All right, anyway, that's a brief review of how removable discontinuities and non-removable discontinuities work. In order to identify the discontinuities, we really need to rewrite everything in factored form. So this numerator would be the same thing as 2 times x minus 2. The denominator factors, this is the difference of two squares. So we have x plus 2 times x minus 2. So we are going to have two discontinuities. Notice that we have a common factor of x minus 2. Because of that, we will have a removable discontinuity at x equals 2. The other denominator gives us a non-removable discontinuity at x equals -2. Of course, in both cases, we're setting each denominator equal to 0 to come up with the discontinuities. Let's factor number 2 to see what's going on. Well, the numerator factors, it'll be 2 times x minus 2. However, the denominator does not actually factor. This is the sum of two squares. It's unfactorable. The discontinuities will happen when the denominator is equal to 0. So the bottom line is this one won't have any discontinuities. You can see it if you try to set the denominator equal to 0 and solve. You'd have to add 4 to both sides. So you have x squared is equal to -4. Right away you can see that there's nothing you can square that's going to give you a negative number. Squaring something always gives you a positive number. So this has no solution. Or another way to look at it is if you were to take the square root of both sides, you're going to get imaginary numbers. So this has no real number solutions. So that's how you know there will be no discontinuities. We have to be more careful with problem number 3 because of the square root of x part. Looking at the previous two problems, these were rational functions. We have a polynomial in the numerator and a polynomial in the denominator for both of these problems. But 2 minus the square root of x is not a polynomial. So we can still set the denominator equal to 0 to see if there's going to be a discontinuity. So let's go ahead and get that out of the way. If we set 2 minus the square root of x equal to 0, then adding the square root of x to both sides, we have 2 is equal to the square root of x. Squaring both sides, we get 4 is equal to x, or x is equal to 4. So this is going to be a discontinuity of some kind. If we let x equal 4, you can just look back and see if we substitute 4 right here, we have 2 minus the square root of 4. That's 2 minus 2, that's 0. So we can see why this is going to be a discontinuity. But is this a removable or non-removable discontinuity? So another way to think about the difference between a removable discontinuity and a non-removable discontinuity is this. When you have a removable discontinuity, it's just a hole in the curve. So the limit as you approach from the left and the limit as you approach from the right are always going to be the same because it's just a hole. So technically, in order to figure out if this is a removable discontinuity, we have to investigate the limit as x approaches 4. In order to find the limit as x approaches 4, we are going to have to use that technique where we multiply by the conjugate. We're going to have to rationalize the denominator. So the conjugate of 2 minus radical x is 2 plus radical x. And we will have to multiply by the same thing in the numerator, so we are not actually changing the value of the problem. So the benefit of multiplying by the conjugate is that you will always get a squared minus b squared. So in the denominator, this is my a, and this is my b. So I'm going to end up with a squared minus b squared. A squared is going to be 4, and then minus b squared. If you square a radical, the radical goes away. So I get 4 minus x. In the numerator, I have the same thing as before. So 4 minus x times 2 plus radical x. But in this form, you can see that we have the same factor in the numerator and the denominator. We have this factor of 4 minus x. So we can cancel out that factor without changing the limit. So we will have the limit as x approaches 4 of, well, it's really just going to be 2 plus radical x. And this is a limit that we can evaluate by direct substitution. If we let x become 4, then we get 2 plus the square root of 4, which is just 2 plus 2, which is 4. So because the limit as x approaches 4 is 4, that tells us that this is a removable discontinuity. We didn't have to do anything special from the left or from the right. We were able to find the limit simply as x approaches 4. So anytime you can just get a single limit, that's going to be removable. Something is telling me to skip this problem, but I'm not going to. So let's go ahead and factor the denominator, since the denominator is where the discontinuities come into play. So we have the absolute value, we have the absolute value of x plus 2 over, and this is going to factor as, let's see, x plus 2 times x plus 4. Looking at these two denominators, we can tell that we will have a discontinuity at x equals -2, and we will also have a discontinuity at x equals -4. What we don't know is whether or not these will be removable or not removable. if the numerator and denominator were both polynomials, we would be able to tell just based on whether or not factors cancel out. But when you have absolute value and other things, you have to use limits to decide whether or not a discontinuity is removable or non-removable. And the bottom line is, if you have a removable discontinuity, that's just a hole. So therefore, you will have the same limit from the left and the right. In other words, for a removable discontinuity, the limit exists. When you have a non-removable discontinuity, the limit from the left and the limit from the right are two different things. In other words, the limit does not exist when it is a non-removable discontinuity. In fact, let's add that to our notes. For a removable discontinuity, the limit exists. For a non-removable discontinuity, the limit does not exist. So let's go back and test these limits one at a time. I want to start with the discontinuity at x equals -4 because I think that one will be the easier one. So let's check the limit as x approaches -4 of the absolute value of x plus 2 over x plus 2 times x plus 4. If this limit exists, then we have a removable discontinuity. Let's try direct substitution. Direct sub gives us this. If we simplify this down a little bit, well, we have -4 plus 2, so that's -2 inside the absolute value. But of course, the absolute value of -2 is +2. And then we have -4 plus 2, so that's -2. And -4 plus 4, well, that's 0. So we're ending up with 2 over 0. This is not the indeterminate case. If we get 0 over 0, we have to use other strategies. But if we get 2 over 0, this means that the limit does not exist. That tells us that the discontinuity at -4 is not removable. It's non-removable. So we figured out that we have a non-removable discontinuity at x equals -4. Let's try to use the same strategy to figure out if the discontinuity at x equals -2 is removable or non-removable. Let's see what happens when we try to find the limit as x approaches -2. Direct substitution gives us this, but -2 plus 2 is 0. So we're going to end up with a 0 in the numerator and a 0 in the denominator. Since the numerator and the denominator are both approaching 0, this is an indeterminate form, and we need to try something else. Let's try finding the limit as x approaches -2 from the left, and then we will find the limit as x approaches -2 from the right, and we will see if they are the same thing. Focus on this part of the problem right here. When the numerator and the denominator are the same expression, except for one of them has an absolute value and one of them doesn't, the expression will either have a value of +1 or -1. There are no other possibilities. Because the numerator is inside of an absolute value, it will always be positive. So if the denominator turns out to be positive, we will get +1. If the denominator turns out to be negative, we will get -1. Since we are trying to find the limit as x approaches -2 from the left, let's use a test value to the left of -2 and see what happens. For example, let's use x equals -3. Again, the numerator is automatically positive because of the absolute value, but this first factor is going to be negative because negative 3 plus 2 is negative 1, while the second factor is going to be positive. Negative 3 plus 4 is positive 1. So a negative times a positive is a negative, so we have a negative denominator, which means the overall value of this expression will be negative 1. You should do all of that in your head. I just showed it for instructional purposes. You should just look at this and think to yourself, aha, we have the same factor in the numerator and the denominator, except one of them has an absolute value. So these will cancel each other out, but they will either cancel and make a positive 1 or a negative 1. Since the x plus 2 in the denominator is not in the absolute value, this is the factor that will determine whether we get a positive 1 or negative 1. We are finding the limit as x approaches negative 2 from the left, so let's imagine a test value to the left of negative 2. That would be negative 3. Putting a negative 3 right here makes negative 3 plus 2. That's a negative number, therefore we get a negative 1 when these cancel out. And in the denominator we still have the x plus 4. Whoops, let's not drop the limit notation just yet. Now we can do direct substitution. If we plug in negative 2 for x, we get negative 1 over negative 2 plus 4, which is negative 1/2. That's the limit from the left. Now let's find the limit from the right. Again, since we have the same factor in the numerator and the denominator, but one factor has an absolute value and the other one doesn't, these will cancel each other out, but when they cancel, they will either make a positive 1 or a negative 1. It all depends on whether the factor without the absolute value is positive or negative. Since we are now finding the limit as x approaches negative 2 from the right, let's use a test value to the right of negative 2 on the number line. For example, negative 1. This time I'm not going to show it, let's just do it mentally. If we substitute a negative 1 right here, that would be negative 1 plus 2, that is a positive. Therefore, these factors will cancel each other out and make a positive 1. This limit can now be evaluated by direct substitution. Plugging in negative 2 for x, we get 1 over negative 2 plus 4, which gives us positive 1/2. Notice that the limit as x approaches negative 2 from the right is positive 1/2, while the limit as x approaches negative 2 from the left was negative 1/2. Because we get two different limits from the left and the right, the overall limit does not exist. When a function approaches two different values from the left and from the right, that is a jump discontinuity, which is a kind of non-removable discontinuity. So we have a non-removable discontinuity at x equals negative 2 as well as x equals negative 4. Number 5, let's rewrite this in factored form so we can see what is going on. So in the numerator we have x minus 3. Perhaps we will have an x minus 3 in the denominator as well. Let me just go out on a limb and put an x minus 3 here. So 9, of course, is 3 times 3. So actually this will be x minus 3 times x minus 3. Oh, interesting. So guys, this is a really good example to pay attention to. So normally we would simply say, hey, look, because of the factors of x minus 3 in the numerator and the denominator, look how these cancel out. So therefore, we're going to have a removable discontinuity at x equals 3. At x equals 3. We would want to say this is removable, but even after we cancel out these x minus 3's, we are still left with 1 over x minus 3. So then what about this? Well, this by itself would be a non-removable discontinuity. This would be like an asymptote at x equals 3. So which is it? Is it going to be, we've only got the one discontinuity at x equals 3. So is it the removable because these cancel out, or is it the asymptote because of the one that's left behind? And the bottom line is that this is non-removable. So why is this non-removable? Think about it. When we canceled out the x minus 3's, did we really remove the discontinuity? No, x equals 3 is still not okay. This is what is left behind after we cancel out the x minus 3's. But if we were to allow x to be equal to 3, we would still get a 0 denominator. So because x equals 3 is still not allowed, it is a non-removable discontinuity. We did not, in fact, remove the discontinuity. All right, let's move on to problem number 6. This will be the last problem. This one's a little bit strange because they're using a letter to represent a constant instead of using an actual number like 2 or 7. But guess what? We can still factor this even though it's a letter. So we're going to have x plus a in the numerator. And then in the denominator, this is the sum of two cubes. And we have learned that the sum of two cubes will always factor as a binomial and then a trinomial. 2 terms and then 3 terms. The binomial is the cube root of each of these terms. So the binomial will simply be x plus a. We will get the trinomial in part by squaring each of these terms from the binomial. So if I square x, I'm going to get x squared. That's my first term. If I take a and I square it, I'm going to get a squared. That's the last term of my trinomial. The middle term of the trinomial is the product of the 2 terms in the binomial. So this is going to be ax. Man, that looks like a 9. I try not to use the letter A because my A's always look like 9s, man. Ax is the middle term. However, the sign is always the opposite, so I'm going to put a minus right here. So here we factored it. Notice that we have the same factor in the numerator and the denominator. We have the x minus a. This x minus a will cancel out. So this is going to be a removable discontinuity. So there you have it, a removable discontinuity at x equals negative a. But wait a minute, there's one more thing we need to worry about. What if the trinomial factors and one of the factors is another x plus a? You know, x plus a times whatever. Well, in that case, because this x plus a did not cancel out, we will have a discontinuity at x equals negative a, and this would be then a non-removable discontinuity. Because even though we canceled out the x plus a's, the extra factor of x plus a still remains. But guess what? We don't have to worry about that because when you factor the difference of 2 cubes, the remaining trinomial is not going to be factorable. So we don't have to worry about that special case. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.